Where is the bowl, by the way?
In the cupboard down at the bottom right hand under the microwave, or maybe the one next door to that. Hello, year 13s. Hey guys, thanks for coming along. Right, last lesson of transition metals aqueous chemistry today. We get to box this all off, which is amazing. Okay, so today we're going to be covering, I'm going to share my screen with you guys. I'm just going to get rid of that, pop out my chat. There we go. Saves me a bit of bandwidth. I'm not, funny enough, I'm not going to bother turning off my camera because I keep causing my laptop to crash. If you guys, I'll actually get rid of my camera altogether. There we go. Right. Dixon, Tenzi, Winkit, Julian, if you can just say hello on the thing, that'll be amazing. I'm going to hide that one. I will stop my camera there. I don't think it makes any difference to mine, but there we go. So, okay. So we're in the very last section now of aqueous chemistry for Edexcel, and we've got 2 more transition metals to do. It's nice for me to do a little bit of referencing here to previous parts of transition metal chemistry. Zinc is a great example. Yeah, the reason being is it's nice just to recall. It's my new favorite picture, that, by the way, that you just had a bit of a glimpse of there. It's in my lesson. It's nice to mention zinc here in the transition metal block. Now, it's not, now this is the point, which is that there, this section, I should color code that. This section here is are the D block elements. Yeah, definition of D block, an element whose outermost electrons are in the D subshell. However, there is a different definition for a transition metal, an element whose atom or ion has an incomplete D subshell, an atom who forms an ion with an incomplete D subshell, and zinc does not qualify. Yeah, both its atom, which is going to be argon 4s2 3d10 full D sub, but then as an ion, zinc only ever forms as 2+, which means it loses the 4s2, having a complete 3d, which means it's definitely not classed as transition metal. Oh my God, I am loving the dabbing from Tenzi and Julian. I can dab too. I feel like I want to dab. Look, I'm dabbing. Oh, you can't actually see me dabbing, but I'm dabbing. Yeah, nickel, of course, is definitely in the transition metal block. So this gives us an expectation. We can make predictions about things we're going to see. So the main one here, and I like to always extend these to these kind of predictions because they do a lot of this in the exams. So in terms of zinc-wise, we can make a prediction saying that all the compounds and complexes are going to be colorless. Yeah, it has a full D sub. And we can remind ourselves then of explaining colors. Yeah, because what we're saying is, why doesn't, we know that nickel is going to have colors. Yeah, it's going to have colored complexes. The reason being is because it has, during its formation of a complex, the D subshell will split, and due to it being incomplete, key bullet points, incomplete D sub, incomplete D subshell. Yeah, which means when split, yeah, you should actually say when D subshell splits. When D subshell splits during the formation of a complex, subshell splits, the electrons can become excited by absorbing visible light. It absorbs visible light, and then you see the complementary color. Yeah, see complementary color. I like it. So it's nice to remind ourselves of those color things. And of course, zinc does form complexes, which means the D subshell is split, but because the D subshell is full, the electrons cannot become excited, therefore they cannot absorb visible light, therefore they're all going to be colorless or white. I like it. Reflects all light. Okay, so let's now do our notes for nickel. By the way, I'm loving this. This is one of my new favorite things here. I love this. So it's a full set of colors. Now, of course, full set of colors for all the transition metals that we need for Edexcel. It doesn't give you any of the complexes that are being formed, and it'd be nice to actually look at that from an oddity perspective. I think this picture has huge amounts of value, and I'm really liking that. So we'll have a look at that later. But let's box off nickel and zinc, shall we? So, okay, try and give myself a bit of space. Okay, so we're going to do nickel. Nickel. Okay, nickel. We lob on our heart. So we're going to add in something like nickel 2 chloride. Yeah, we know that nickel is always +2, always. Yeah, so nickel is always +2. It's quite nice to actually look at nickel's electron configuration to understand why that is, and we might do that in a bit. But we're going to start off with nickel 2 chloride solid, and this as anhydrous, and I know I'm doing this an awful lot, and I'm really making a thing of this. Yeah, that's going to be going in as a white solid if it's anhydrous. Yeah, anhydrous, it's going to be white. Yeah, not colorless, by the way. Colorless are for solutions. Yeah, colorless is for solutions, but white is for the solids. So it's going to be a white solid. Right, the first thing we're going to do, of course, is we're going to add water to this. We run the usual process, add H2O. We don't actually need the word add because we know that all of these arrows are additions. So let's just put H2O over it. Okay, now guys, I know that we've talked about the colors of nickel a little bit in various Google Meet chats. So it'd be nice for you guys to take this as an opportunity to do a bit of color recall. Yeah, we know the process. Add water, add a little OH minus, little minus excess, sodium hydroxide excess. Then we're going to add ammonia little. Yeah, and the little's always the same. I love that. Always focus on the routines. The two littles are always the same, both for color and complex. I love that. Makes my life so much easier. Then we're going to do excess ammonia excess. So that's a concentrated scenario. And then we're going to add our carbonate ion. The great thing is in terms of nickel, I don't believe that there are any oddities for the nickel. Nickel does form a chloride, I believe, and we'll have a look at that at the end of this. But there aren't really many oddities for nickel. Nickel just kind of runs as normal. So what I'd like you to do now, guys, is pause the video. And what I want to remember is nickel is a 2+, which gives us some routines and some patterns that we're never going to. I want you to fill out the ones that you can definitely be absolutely sure about. Yeah, and if you've got any doubts, just don't fill that one in, and then you can unpause the video and fill those in as I do so. So first things first, we are going to form the nickel hexaraqua. Good old nickel. Nickel hexaraqua, 2+, and it picks up its first color. And in this case, it's gonna be green. So it's a rather nice green. It's like an olivey green, quite pale in reality, and it's nice to remember because it has a charge. Yeah, any transition metal complex with a charge in solution is going to be aqueous. I always love that. Next, the OH minus little. So I think this is fairly self-explanatory. We've picked up this routine already. The 2+ tells us how many of these it's going to need. So it's going to need 2 of them. That's in the equation. It's nice to mention that. That there is the equation section. Yeah, the role is going to be a base, a Bronsted-Lowry base, and we're going to form the tetra-aqua dihydroxy complex. It loses its charge, yeah, so it becomes a solid. It loses its charge because the OH minus ions are going to cancel out the 2+ in the hexaraqua. So it becomes, and this becomes a green solid. It's slightly darker, not by a huge amount. In reality, you'd actually argue, some here would say that they are actually the same. It's a very, very, it is a slight, it's more luminescent than, I'm going to try and put it like as that one kind of thing. It's more of a luminescent green. So you don't need to say darker. You don't need to add any particular color to this. There's no emphasis on a darker. This is simply, it forms a green precipitate. The next thing is, in terms of excess sodium hydroxide, nickel does a very typical thing, because one of the things I said was trying to apply these rules of the 2+. So if I just quickly pick some of these up, I'm just going to highlight them in green. So manganese 2+. Yeah, manganese 2 plus is there. So manganese 2 plus starts off as pink. It forms like it's a cream-esque, a pale pink stroke cream precipitate in the limited, in the little sodium hydroxide, and doesn't redissolve on excess. Let's look at another one. Iron 2 plus with limited forms the green precipitate, but then on the excess, it doesn't. By the way, there's an error in this particular diagram, which is here. There's the error. Error. You don't get the browning in limited. You only get the browning in excess. Yeah, that's correct, but not for limited, not for little. You don't see it because it's not in an alkali condition. But notice the 2 plus hasn't redissolved. Let's look at another one. Let's go back to another one. Try to use the same color here. So if we go to nickel 2 plus, right, nickel 2 plus forms the green precipitate and doesn't redissolve. The reason for this process, the reason why they don't, you can do this for copper as well. So for copper, it starts off as a 2 plus, it forms the precipitate, and then it forms the same precipitate. That's an error as well. It is not a deeper blue. Yeah, there is no difference there between them. There's another error. Yeah, I love this picture, but it does have a couple of anomalies there that do need to be discussed. But the 2 pluses aren't dissolving. There are a few here that break this rule. Yeah, the zinc is one that breaks the rule. Notice that cobalt doesn't either. Look at the 2 plus. So we start with the pink hexaqua, then we form the blue PPT on the little sodium hydroxide, and it doesn't redissolve on excess. Yeah, so the 2 pluses aren't doing it. Zinc breaks that rule. Like I said, the iron 2 has got this rather interesting anomaly for the 2 plus because it darkens, but it still doesn't redissolve. But the point I'm trying to make is there's a rule here. 2 pluses are not acidic enough. That's the point. The 2 pluses, it's a great rule, are not acidic enough to be able to redissolve on excess sodium hydroxide. So they continue to form the solid, and it's the same solid that's seen in the little. And this is great. We like this fact. Yeah. Next is ammonia little. The ammonia little is always the same because in this case, their roles, and we can put in the 2 there as well. So this star, we can put in this like little bit of a hint here. This star, which I've got over here, yeah, I'm just going to make those disappear. So that star, go away. Oh, just go away. There we go. That star tells us that the role of these 2 is the same. Yeah, for little OH minus / ammonia, role is the same. Role is Bl base. Yeah, they're accepting a proton. So they have the same role. I'm just going to put same role. Same role and underline Bl base. Okay, so the great thing is it's always something that we can rely on. There are no exceptions to this rule. It works well. We like it. Yeah, there we go. Another solid. Tetraaquid dihydroxy. Now we do get something different at this point for nickel. So if we come over for nickel for excess, you see in the excess, the precipitate has vanished. You no longer have the speckles that you see here. So nickel is redissolving. And this is following a similar routine to both cobalt and chromium. Yeah, both do this. And they both, so it forms a green solution. And it is a slightly paler green again. It's a bit, as I said, by the way, I love nickel because you can just call them all greens. But nickel does the similar thing. Oh, there we go. Full swap. Full switcheroni. Yeah, it gains its charge again. Therefore, it becomes aqueous and it forms a green solution. And it looks a bit like that again. There we go. Forms a green solution. So green, all the greens, And then lastly, of course, it does exactly the same thing, which is going to be with any 2 plus. This rule always applies as well. This is a solid rule, and we're going to form nickel 2 carbonate. I like it. So just quickly, I mean, it's a bit ridiculous, isn't it? Because you can then see all the greens. And that's one of the best things about nickel, just to point these ones out. So we've got nickel hexaqua, we've got nickel with sodium hydroxide little, nickel with sodium hydroxide excess, nickel with ammonia. It's always going to be the same as the little. And then we get this pale green-esque nickel with concentrated ammonia, and then the nickel carbonate. So they're just all greens. I just want to show you the nickel, the hexamine, because it's quite a nice thing to actually see this one. So nickel, let's do nickel, let's do hexamine, double M because it stands for ammonia, hexamine nickel 2. Let's go for that. Images. Ooh, look at that. It's gone purple. Giving it as, oh, it's a blue. No, is that correct? Yeah. Ooh, okay, guys. So it's not green. I tell a lie. Ooh, it's blue. And I do remember that because it has a similar blue to cobalt. Somebody comment on the chat. We chatted about this last time and I've totally fumbled that one. That's irritating. So it's gone blue. Let's add that into our notes. So there's a mistake in the diagram. Yeah, it's blue. It's a pale blue. It's not even a pale blue. I do apologize, guys. Get rid of that. There we go. It becomes a blue. It's actually darker than copper 2 sulfate originally. Yeah, it's not, but you wouldn't actually call it dark blue. You don't really need to. So there's me making an error. I hate it when I make mistakes. So many colors. Green, green, green. 4 greens, blue, green. Green, 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 blue, green, colorless. Yeah, well, you don't need to include the last one at the beginning because it's not something I ever talk about. But definitely one to focus on there, guys. I do apologize. I hate when I make mistakes. It's funny because I did know to check it, but I still would say I definitely fumbled that one. Okay, so bear that in mind. Do you know what? I'll make sure that we come back to that and we find some questions from Edexcel that come up and repeatedly trying to fix that into our minds. Yeah, for sure. So, yeah, I have to say, do you know what I might do? At some point or another, I'm going to sit down. This has been done in Paint, of course, but there is some value in this, and I want to actually take that diagram there and fix it for all its errors. It'd be interesting. It is a definite blue, and that is not what it's saying there, which is frustrating. It needs to be corrected. Okay, let's go for the next one. Zinc. Oh, zinc. Okay. Let's see if I can make no mistakes in this one. So we've got, oh, I've suddenly realized I need to put it in a heart. Let's go to our heart. Zinc. Zinc 2+. That was a terrible heart. Ooh, better. Okay, so we're going to start with zinc chloride. By the way, because zinc is always 2+, you don't tend to use the Roman numeral in its naming. We just call it zinc chloride because it's always +2. So this, of course, is a solid and it's white. Yeah, a white solid. Definitely added to your notes. Have I made my notes bigger? No, it's all right. It's irritating. There we go. So it's a white solid. Okay, we're going to add it to water. And like I mentioned at the start of the lesson, they're either colorless or white. That is how it works. There's no colors here. It is not classed as a transition metal. So we're going to add it to water first of all. You guys can now pause the video and complete. Zinc hexaaqua. Hexaaqua 2+. It has a charge, therefore it's aqueous, therefore it's going to be colorless. Yeah, it's a colorless solution. And I'm going to try and make that as pale as I can. Yeah, a colorless solution. There we go. So this is a colorless solution. Colorless sol. Okay, usual gig. We know this routine now. Once again, guys, if you want to now continue, and this is little. Yeah, if you want to continue and fill in some of these, you can certainly do the littles. Yeah, OH- excess, and then we have the 2 littles, of course. I love the littles, it makes me so happy. Little, and then we have ammonia excess, conc, mentioning conc again, and then the carbonate, CO3 2-. Okay, so everyone here will be able to do this one. Zinc brackets, H2O4, tetraaqua dihydroxy again, and this is now a solid. and it is white. It's a precipitate, a white precipitate. So we had a colorless solution, we're forming a white precipitate. So white PPT. No, I think I want to actually write it down in black. A white PPT. Gelatinous precipitate. I'm going to do colorless solution. I'm going to write it underneath. I think it's better. Colorless sol. Okay, next one. Now, this is where zinc is an oddity. Now, people often ask me why zinc here is an anomaly in terms of the 2 pluses. Because we realize that the 2 pluses in general don't redissolve. However, zinc does. The reason for this is we know that as you move across from left to right across my periodic table, I'm going to shrink my pen down. It's ridiculous how fast it is. As we move across the periodic table, yeah, the atoms, we know, all shrink in size. Yeah, we know this. They get smaller and smaller and smaller and smaller and smaller and smaller, etc. Yeah. There we go. They shrink in size. Now, what this means is that when you get to zinc, we are more than halfway across the table, which means the ion of zinc 2+ is relatively small. What this means is it means its high charge density, yeah, makes it behave a bit more like a 3+ ion than a 2+ ion. And I know copper doesn't do it, which is odd, and zinc, the fact that zinc does, but it's just the way it is. And as I said, it is to do with its charge density becoming high enough. Now, it's nice to say that copper doesn't do this. Yeah, copper does not redissolve. There is no change on excess, but zinc goes through a small change. It's not a massive change, but it goes through a small change. And you'll hopefully understand what I mean by this. Zinc, and this is an oddity, right, 2-. It's a strange one. It kicks off all the waters and attaches 4 OH- ions, and it actually becomes it's not a solid, Mr. Duncan, it's charged. Yeah, any charges mean it's aqueous. What that means is you actually form a tetrahedral complex, which is a rather odd thing that. Yeah, it forms a tetrahedral complex like that. And because, of course, it's now 2-, it redissolves. If you gain a charge, you become soluble. Yeah, you have ion dipole interactions, which means that the enthalpy released from hydration is higher, therefore it becomes soluble. Yeah, so I don't know why I deleted it. I quite like, is it worth, yeah, I'm just gonna leave it there. There we go. So you form a tetrahedral complex of the hexahydroxy zinc 2+ complex. Yeah, and this is a colorless solution. It redissolves. Colorless sol. Okay, next. I should actually just, it's nice to show the difference between colorless and white. So yeah, I prefer that. That's better. Next, the little, of course, exactly the same thing. Zinc, exactly the same thing as the other little. Sorry, just remember that. 2 littles always behave the same because the role of the ammonia and OH- is the same. They are bond-Sadlari bases. So learn the patterns. Yeah, tetra aqua dihydroxy solid complex, gelatinous precipitate. And it's white again. Yeah, there we go. A white PPT. White PPT. Right, next, what happens on excess? So on excess, it redissolves as well. And it does exactly the same thing that it does with the hydroxide ion. Yeah, so it actually forms a tetrahedral complex, which is, it's nice that zinc has a little bit of this continuity about it. Let's have a look. Let's do delete. Oh, hang on, there it is. Oh, oh, that's nickel. So let's now go zinc, excess ammonia. There we go. So it's an oddity, but the great thing is that the oddity is in the 2 excesses. It's not, and there is huge value in that. You learn one anomaly, yeah, learn that anomaly, and then go, oh, zinc does the same thing with the ammonia ion, yeah, with the, oh, gotta be careful, with the ammonia ligand, Yeah, zinc, Zn, same routine. But, and so yeah, sorry. There we go, that's better. 4, only 4. It's not, if it was a 3+, it'd go to 6, but it doesn't. It's a 2+. It's not quite attractive enough to form a hexamine complex, but this time forms a tetraamine. And once again, it has a charge because ammonia is a neutral ligand. So this becomes a colorless solution, colorless sol. So there are some odd things. That's a weird thing, that right there. Yeah, that there is a very odd thing for zinc. Recognizing that it does this from a 4 perspective rather than a 6. This is why you've got to learn them. And of course, the last one, you form zinc carbonate. It's a 2+. All the 2+, of course, form their carbonates. And surprise, surprise, it's white. A white PPT. There we go. It's a white solid. You can write that underneath it, white PPT. Cool. And that brings us to the end of aqueous chemistry, transition metals. We have covered all of our people. I know it's an awful lot, guys. And all I can say is learn them as strings. And I'm going to mention the strings now, actually. At this point, I've ticked off. Yeah, and we've mentioned zinc at the oddities, the odd excesses, yeah, for both of them. We've picked up that nickel forms a blue solution in the presence of excess ammonia. I want to just talk about this idea of strings, because learning these colors is hard. I mean, we can actually point out, so how many do we have to learn? We have to learn, I'm just going to get rid of all of these. I might even set you guys a homework to do this for me. I think there'll be massive value in them. Yeah. And what you can do is you can do it rather than, I'm not a particular fan of how this moves around. Yeah. But I understand why they've done it like this. What I would prefer is a diagram of each of these. Would I? It becomes more diagrams, but then it helps you create the strings. What I would do is each of these, yeah, the string. Let's talk. I'm just going to, sorry, ranting. Okay. To learn colors, to learn all these colors, it is easier. Use color patterns, color strings. That seems weird. I'll explain. Pink, blue, 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 straw, yellow, pink. Use color strings. So cobalt 2+. Yeah. What we do is we realize that the table is handy. We're going to do 6 colors for each of them. We know that there are anomalies as well, oddities and extras. But what we want to do is, because they look at this, the majority of the time they look at this from a perspective where they step through the processes, doing different things in these flow-like diagrams. So the learning these as a string is very handy for that. It actually supports those questions. So we're going to do water. We're going to do OH minus little. We're going to do OH minus excess. We're going to do ammonia little. You realize that I've been, the little hearts that we've been working through. Yeah, I've done them in the same pattern every time. Yeah, I'm trying to encourage this idea of these strings of colors. And we would go pink, pink, blue, 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 straw yellow, pink. There we go. So you learn them as a string of colors, because that's 6 colors I've just done. Pink, blue, 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 straw yellow, pink. Yeah, we know that cobalt has a little bit of an extra. We'll learn those separately. Those we learn as a flashcard, if like cobalt chloride. Yeah, so we can use cobalt tetrachloride as a test for water. So what happens is, of course, you start off with cobalt chloride being blue, so extras. Extra CuCl4 2 minus, yeah, CoCl4 2 minus, and that's blue. And then what you do is you add water to it and it turns pink. Yeah. Others for cobalt is we know that these darken. The excesses of both, yeah, darken. So that one genuinely darkens. That one goes from a straw yellow to a color for this. Yeah, you don't actually need the color for this. All you actually comment on it is that it darkens. It's allowed to say darkens. Whereas the excess sodium hydroxide actually becomes this pale brown precipitate. It does actually become a similar one to that one. Yeah, I know it's odd that, isn't it? But yeah, but they allow you to say darkens, which is crazy. So learn them as strings: pink, blue, 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 straw, yellow, pink. Purple, green, 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 purple, green. It's not purple at the beginning, it's violet. Cobalt, chromium, sorry, chromium 3+. Yeah, learn them as strings. Purple, green, 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 purple, green. Yeah, purple, green, 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 purple, green, purple, green, 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 purple, green. But it's not purple. It's violet. At the beginning, it's not purple. It's actually a violet-like color. It's like that. The annoying thing is you're going to go, it's the same color. Oh, it's really annoying. You have to call that one violet. Yeah. And then you pick up chromiums on T's of there. But the point I'm trying to make is these strings enable you to learn colors in chunks. Yeah. And that's what I would recommend to do. Create yourself some flashcards. Green, 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 blue, green, done. Anyway, you kind of get the idea. So that actually brings aqueous chemistry to a close, amazingly. I'm going to end my video there. So your homework task, what I'd like you to do is to create these strings of colors, yeah, and put them onto flashcards that you can just repeat so that they become lodged in your brain. And you really do need them. You do. So important. Let's go to StreamYard. Let's bring this back. Start camera. Stop sharing my screen. Right. Okay, guys. I hope you found it useful. Next lesson on Wednesday. So I'm going to set you your homework, which is, this is just a self-assessment test. It's a short test purely on aqueous chemistry. No complexes, no nothing. However, on Thursday, you have your full transition metal test, which will include complexes. So your complexes as well. So what that means is you need to revise the test I gave you on complexes, look through it, watch the YouTube video of the exam review, go through those, have a look at them, come up with any questions that you've got over the next couple of days. Yeah, have a go at the homework that I'm going to set you in terms of a test-wise, and I want you to do it and then mark it yourself, and then I can answer any questions you've got on Wednesday. We're going to do one lesson focusing purely on exam-style questions of these transition metal aqueuses on Wednesday in preparation for your test on Thursday. I hope you find it useful, guys, and I will see you all on Wednesday.